Hello, it's James from xrobots.co.uk. This is part 4 of Robot X, the reconfigurable sci-fi robot. We spent the previous 3 parts putting this together, and this is made of 3D prints in ABS and ColorFab HT, which has excellent layer bonding properties to make lots of the mechanical parts, and also aluminium 2020 extrusion, so the whole thing can easily be reconfigured. Pieces can just be unbolted and swapped out as we go. And we've got pretty much the body on here. There's another actuator to go to tip the body backwards and forwards, and some other things we discussed last time. I've got some of the electronics installed and the actuators installed, so we're pretty much ready to wire this up and get it working. Have a look at the previous parts of the build and also my Gonk Droid series to see another walking robot that I built in the previous series. Effectively, this is the next generation, and hopefully due to its configurable nature, or its reconfigurable nature, we won't have to rebuild huge parts of it if we need to change it. As I say, we can just unbolt parts and just make small modifications, so this should be the ultimate robot. Obviously it's a two-legged walking robot that's quite complicated, but I can use this for R&D to test the best way to make it work. But before we get started, I wanted to just revisit those actuators. So the actuators I've used here are drill motors, basically, with a chuck with the lead screw in the chuck and a nut in this thing here. So we do have some issues with flexibility, and this isn't really the way you're supposed to use lead screws and nuts. There should be a parallel rail, really, with the nut going up and down with a proper carriage and the actuator attached to that. But I need these to flex at both ends, and I thought it'd be really simple. So we do have some problems here, really. And I've been waiting for some extra nuts to arrive so I can put 2 nuts in each actuator, and we left provision for those in the hips. And those have now arrived so we can install them. The other concern is about the chucks coming undone because they're keyless chucks, and whether the lead screws will just fall out. So in the hip actuators I left this hole here so I can insert another nut facing the other way, and we looked at testing that with some spare nuts last time. Obviously it'd be ideal to have the nuts as far apart as possible to prevent that lead screw moving too much around that axis, but when the lead screw is right out, it's right at the end, so putting the nuts close together is the way it's going to have to be. I could put 3 nuts in total, and that would help me when the lead screw is screwed in. I also took the opportunity to tear down one of these drills a little bit and take the plastic off the keyless chuck, which is obviously 2 sections you twist against each other. So the back piece came off fairly easily, and it was just fitted on that bit of knurling there. The front one was a lot harder to get off. It was attached very well, and I probably could have left it there. But the basic plan is to grab that back piece and this front piece with wrenches and do them up really tight. Obviously I could take the chuck off, and I could take the torque gearbox off here and see what's right back in there, but it's likely the gearbox has got a very small shaft on it. Obviously the chuck and everything in here is designed to hold something dead straight, and it will take quite a lot of beating because it's a drill. So for now I'm going to leave the chucks on and just do them up really tight with a wrench. So let's get on and make both those changes. So I fitted all those double nuts. There's still a bit of play in the leg. It's not totally great. I might have to completely redesign the actuators with proper rails and everything, but that's no problem. I've basically taken the plastic off the bottom chucks and done them up super tight. The tops I've just done up with wrenches, but I could strip the plastic off and do them even tighter. We'll see how it goes, but actually I think it's probably going to be alright for initial testing. It's now time to do some electronics, so we need to run wires from the electronics all the way down to all those motors and pots. So we're getting there with the pot wires wired in. Each one of course has 0 and 5 volts, and the blue wire is the signal from the wiper in the middle that gives me the position. I've made some 3D printed little clips there, which we've got a thing so I can cable tie the cables on. Those cables go all the way up to the top here, where they eventually go to the electronics. Next is all the motor power wires, which need routing up to those motor drivers. Those are all my motor wires, and they come up on these big loops because of course the body is eventually going to move backwards and forwards, so we need to leave enough slack. Same with the legs here, so all of these wires reach the motor drivers in the body. So here's the other end of those pot wires. All of those pot wires come into this breakout board so I can probe them and test them, and they go to the analog ins on the Arduino here. I've got 3.3 and 5 volts coming around to a distribution panel. So we've got 3.3 volts at the bottom that go to the pots. Because the analog ins are only capable of measuring up to 3.3 volts, so we need to make sure we're only putting 3.3 volts on them, which is the maximum that will come back. Now all of those pots are 10k, and there will eventually be 10 in parallel, which is 1k. So at 3.3 volts it only draws 33 milliamps, which isn't very much at all. So that's fine. We're using the 3.3 volts off the Arduino, so the regulator on board, and this will be powered by 5 volts. It's a 3.3 volt device, but it has its own regulator, so that's providing the 3.3 for the pots, which should be fine because they hardly draw any current. 5 volts going to our PWM controller. That still needs to be cabled into the motor drivers, and we need to cable I2C from the Arduino to the PWM driver to get the actual signals out. I've connected the I2C, but in order to do so I've had to use level matchers, which is what these are. So the Arduino pins, as I say, are 3.3 volts. This is a 5 volt device, so we've got these level matchers, and I've left enough here to deal with some other serial devices like the Bluetooth remote and the IMUs I have to put in for stability. So the level matcher takes 3.3 and 5 volts and ground, and then it will change 3.3 volt level things to 5 volt level things. So we've got just I2C for the servo or the PWM driver cabled in at the moment, but there will be more things in the future. So I thought it would be a good opportunity to put some code on that board and check the PWM board works and the level matching works and everything works before I go ahead. So I mentioned the board is a clone of an Adafruit board. This is the learning guide for the Adafruit board with a hookup and everything for controlling servos and controlling PWM devices. And I found in fact that I couldn't get it to work with the example library, and in fact what the issue is that there are two I2C interfaces on the Arduino Duo that I'm using, and I'm using the wrong one, so I've moved that over and then everything worked. So this is the example code for PWM driving. So it uses the wire library for I2C. Adafruit have got their own library for this board. So it's pretty simple actually. You've got a PWM carrier frequency there, and then there was a loop in this library which basically went through each of the 16 PWM pins and ramped them up and then back to 0. I've simplified that slightly with just a small for loop, which basically takes this value, so that will be the pin value, and these are the two PWM values. If you leave the middle one at 0 and just give this one a value between 0 and 4096, so it's 12-bit, then that will ramp up the PWM basically, and a small delay there, so it just counts through. So if we look at this now, we can see we get the voltage rising and returning to 0. Okay, so I'm just powering this off a USB boost adapter at the moment. I've got my multimeter here connected to one of the pins on the driver there, and we should be able to see that that's ramping up nicely and then back to the beginning again, so that's just counting through. And the next thing will be to attach that to a motor and check that my motor drivers work with this PWM, and I think there'll be no problem, but I'm going to do that before I wire everything up. So I've just got a test running here with one of the cordless screwdriver batteries, one of the motors, one motor driver and one PWM channel, which is still ramping up there as you can see. And when it gets to the top it stops dead and then it starts again. So that seems to be working pretty well. Pretty glad that all of that hangs together and I can control the speed of the motors okay. Well, there it goes. And of course I've got the emergency stop button which cuts the enable. That's just the other end of that's wired to 5 volts for now, so if I hit that at any point it will cut all the motors off. And I also have the individual enable switches I wired in last time, so I can switch off individual motor channels. But that seems to work pretty well. So these red and black wires are the 5 volts and ground that go to every motor driver to power the logic on them, but we actually need to wire in the battery to power all of the motors, so that's going to fit in this middle section. But we need to actually run power to all of those motor drivers, and we need to put switches and fuses on it. So we're going to use LiPos to power the actual motors. I've got 4 here, which are 5 amp hour each. We use one of those in the Gonk Droid, and 4 in BB-8 in fact. So don't know if 4's enough, but I could fit more in. I'm reluctant to buy any bigger batteries because they're quite expensive, so we'll see how we start with that. They do come up to 20 amp hour, but these are about 30 or 40 pounds each in money anyway, and I've already got them. So those are going to run in parallel in 2 sets, one for the left-hand side of the robot and one for the right-hand side. Each set is going to have a fuse. This is a 40 amp blade fuse in a holder. And each one is going to have a switch, and I've got these rather attractive switch covers, which are like rocket launching ones, where you do this and turn them on, and then when you flip that down, that cuts the power, so that's a bit like an emergency stop. These are 10 amp toggles, but they're 2 pole and each pole is 10 amps, so I can switch 20 amps with these. But hopefully I won't have to switch the actual current off while it's running, so they'll handle more current in one position, and obviously when they're off they'll handle no current, so that's fine. So I think this is probably an okay size fuse. It allows 10 amps per motor, and really I'm just worried about fusing it. If something shorts out, that will draw lots of current and blow the fuse. Well, it's not amazing looking, and these fuses can't really stay hanging around here, so probably need some chassis mount fuse holders instead. But all of that's wired in, all the power's wired to the motor drivers, and my switch switches on each pair of batteries. So the next thing is to write some code, but I just wanted to sort out all of the pots and read those in first before we try and set up PID controllers against them. So I've just got a very simple sketch here. I've just written in the pots as integers, and basically we're going to read all those analog values. We've got a 12-bit resolution here on the analog instead of 10-bit, so our variables will go up to 4096. It's quite good to have the extra resolution because those pots, of course, won't do anywhere near their full turning circle of 180 degrees because the legs aren't going to move that far. So basically I'm just writing these out to the serial terminal, and we can see they're all roughly in the middle there. They're around, most of them are around 2000. I tried to put the pots in as straight as I can. Some of them got rotated when I did up the grub screws on them. So basically the plan is to take away this value. I've posed the robot in a neutral position. We'll take away this value, and that should zero them all, and they should all swing about zero as well, with a 2048 swing, positive and negative. Right, I've set up my first PID controller, and I'm not going to go into too much detail other than to say that the PID controllers are running against the pots. So for the first PID controller, the input is pot 1 and the second one is pot 2. I've set the set points to 0 at the moment, which is that midpoint on the pot after the calibration has taken place there. So right at the top I've got some defines that put all the offsets in, and further down I'm basically taking those offsets away to give me 0 on the pots. So the crucial part is the motors, of course, are not attached directly to the pots. There's two of them pushing across those axes. So motor 1 essentially there is taking the output from PID 2, which is the front to back pot, and then it's taking away the other output, which is the side to side pot. And motor 2 is the opposite. So again, the output 2 there is driving it backwards and forwards. So those are both effectively positive or negative values at the same time. But instead I'm taking away that side to side pot. So the side to side pot is essentially pulling and pushing, whereas the front to back pot is pushing both of them at the same time. And that basically the output of those motors goes into an if statement to say if it's less than 0, turn the motor one way, if it's more than 0, turn it the other way, and that's the same for both motors. So now we can see that that will automatically sort of center that leg around 0 for both pots. So the quick recap is we've got two pots here. The one on the side here will add and subtract the value from both motors at the same time to push forward and backwards, and this one will add from one and subtract from the other, so that will mean the motors push and pull, and that moves the ankle sideways. So I've just offset the position manually by turning the lead screws of that ankle, and now I'm going to pick this up off one leg off the ground and turn the motor enable on, and we should find the motor centre because the set point is set to 0. Yep, there we go. Right, I've now configured up all my PID controllers for each of those 4 pairs of motors and the 4 pairs of pots. So all my 16 PWM wires are wired in. The only other addition to this is I've added some little voltage readouts for the 2 sides of the droid. So we've got the 2 sets of batteries in parallel. I've only got 1 battery in each side at the moment for testing, but I can monitor those voltages. Eventually we'll read those voltages as an analog in, and we'll vary the motor speeds so that we can actually make the max motor speed increase as the battery goes flat, so everything stays consistent. I've tuned those PID controllers up pretty tight. They do need to be tuned down. We need to put some motion smoothing in, but if I go and enable the motor enable with the big emergency stop and we give it a shove, we should find the oscillation just causes it to jump from side to side there, so eventually it'll settle. So we need to tune that out, but basically the flex is in the robot is flexing the pots, and then they're trying to compensate by moving back the other way, but it's going too far, so it's overshooting, and it sits there hobbling from side to side. The next thing I want to do is tune that out, possibly put some motion smoothing in. We'll see how it goes, but definitely that'll exist in the future. But the next thing is I want to be able to send commands to it to bend the legs, lean side to side and everything, so that we can check those perpendicular pot axis and the PID controller mixing is working properly. Right, the next thing here is to try and get some commands sent to the robot to make it do various things. So I'm doing a serial read here. I'm doing a parseInt, and then looking for the new line. And basically I'm using a parseInt rather than a byte read because I want to be able to type these in on the serial console, as well as eventually having a remote that sends the data over Bluetooth. So I'm going to send one integer, and then I'm stripping out the individual bits. So using bit read from that variable, we can then get buttons that are 0 or 1, which will relate to the remote control. So I've got a counter here that counts up all the time, and that's just there to check that the loop is still running and it's not hung on serial reads or any timeouts. And then I'm writing those out to the console. So now if we go and get the serial monitor, we should find our count goes up nicely on the left. The number here is going to be the number I send to it, and these are all the bits. So if I send 64, we should get the far right bit turns on. Obviously these are the other way round to what they would normally be. Normally that would be the least significant bit. 1 is at the other end, of course, and of course 1 and 64 will give me both of them. 127 will give me all of them, and somewhere in the middle we'll just get 1 depending on what value I send to it, so we can get the remote to do exactly the same thing. And I've just got some if statements that change the set point for all the PID controllers. So if button 7 is depressed, or I send 64 to it, then it will bend all the legs, and then if it's not pressed, it'll put them back to the middle. And then if button 6 is pressed or button 5 is pressed, that will make it lean one way or the other. And if neither are pressed, it comes back to the middle again. I've made this remote control, which has got 7 buttons on. In fact, it's got 2 switches and 5 buttons, and those send the same bits. So this basically transmits the same integer. It's got a Bluetooth interface. It's flashing away there, and an Arduino Pro Mini, and that just sends the same integer into the same serial port. So I can either type it in on the console, or I can send it remotely by pressing these buttons. Alright, so we can now use the remote to trigger some functions. So I've coded up some rudimentary motion control. We've got a bit of motion smoothing just in the PID controller by using proportional only. And it can bend its legs and do a few things. So now if I press that button 7, we can make it crouch down and back up again. And I can make it lean side to side with these 2 green buttons. So obviously there's no stability control. We're going to put an inertial measurement unit in it next time. But for now I'm pretty happy with that. I'm running the motors about quarter speed. So we've got quite a lot of scope there to basically increase the speed effectively or compensate for the battery going flat. So I'm pretty happy with that. You'll notice that when it is crouching down, it's quite unstable, quite a lot more unstable than when it's standing up. And obviously that's due to the angle of the actuators and the angle of the legs, so the actuators can rotate in that axis, which is kind of similar to the way it's leaning backwards and forwards. But fortunately it doesn't have to really do that to walk. One leg will always be straight and one will be bent that's picking up, so it should be stable on one leg. Obviously I still quite like to redesign these actuators somewhat, but they'll probably do for initial development, and hopefully we can get some steps out of it before I have to redesign them. I just wanted to add as well that the squeaking you can hear is one lead screw, which is actually slightly bent because I overdrove it upwards when I was testing. I got the axis the wrong way round, and that's now bent, so it's squeaking in the 2 nuts. So I need to replace it, but I don't have another one to replace it with right now. But basically it's quite interesting. It bent the metal rather than breaking the plastic, so pretty happy with the structure overall. Alright, that's all from Robot X for this week, but don't forget to check back for the next Ultron episode next week. As I say, in the next Robot X episode, I'm going to be putting inertial measurement units into its body and its legs so we can set those precise angles in space and make sure we know when it's got there rather than using timers like we did in the Gonk droid. So hopefully we can get into a position where we can make it lean side to side, picking up the opposite foot as it does so, and that's the first step towards walking along. We've got a few mechanical and electronic tweaks to make, but I'm pretty happy with the way this is going as it is at the moment. So don't forget to subscribe for more updates on this project and other projects. Also check out my Patreon campaign at patreon.com/xrobots, where you can get access to some exclusive rewards, including all my videos early and a live broadcast with me. Also check out my Spreadshirt t-shirt store for X Robots t-shirts and other merchandise. Alright, that's all for now.